journey over Zergi, so please accept my apologies because this presentation is a little bit extended necessarily, and you'll understand what's here going. I'll try and not make it get back whole quick if I can help it. Okay. So I thought it would be useful just to give you an understanding of SDFC, what we are, what we do, and our role within this particular circle, and generally our thoughts are outside within the Agri network. We're actually a large multidisciplinary organisation. We have people coming in from various disciplines, essentially to use our facilities. We build, design, maintain, operate large facilities for the benefit of the UK's research base. So it's a service that we provide for the UK's researchers. The UK has 7 research councils, such as BPS, RC, and so on. And they're funded by the government. And they fund essentially research within their particular disciplines. And also STFC does some of that, but a vast majority of our effort goes into providing the large-scale facilities for the UK. So effectively, what we do is support some of the science that goes on through the other research councils. So we actually sit within that research council circle, so the 7 research councils. Large-scale facilities, all of our campuses, because of the high technology that goes into providing those facilities, because of that technology, the campuses are starting to become hubs of science and technology expertise, and so they're going from that area. Also, more and more now we're being asked by government to provide evidence of impact. So this is not just necessarily economic impact, but it's impact in a wider sense, so health and well-being of the population as well. We've got a number of campuses around the UK. I won't go through all of them, but essentially, if you look at the top left-hand side, that's the Daresbury campus. That was where the world's first synchrotron was built, and that's where we still have a lot of our particle accelerator capability. We also have the UK's high-performance computing capabilities there as well. And if we come down to the bottom right-hand side, this is the Rutherford Appleton Laboratory. It's probably the largest one that we, well, not probably, it is the largest one that we have within SCMC. We've also got various other ones dotted around, which I shan't go through. So the main thing that we provide are new things like neutron sources, high-power lasers, and other light sources. We also look after the UK subscription and interest in international collaborations, such as European Solar Observatories, etc. And to give you an idea of what the Rutherford Appleton Laboratory looks like, this is an aerial shot of the campus. So that's the synchrotron light source. We have ground space co-located on 2 areas, one here, and actually it's a bit of an old shot, I think. There's another one here just been formed. European Space Agency here, neutron source here, and then we've got another European Space Agency building just built recently here. So it's a fairly large campus, and 3 main facilities available for use by the visitors. The central laser facility has a number of laser systems. I'll start with the high power one. So Vulcan is the high power laser that we have. It's a petawatt laser, that's 1,000 million watts of power in a single pulse. It's quite a new technology now, and that's being superseded by this one here, which is now starting to produce similar sort of powers. On the right-hand side are the laboratory type laser systems. So the Ultra is a pump probe system. We can produce pretty much any wavelength with any pulse width going from femtosecond through to continuous wave, and with any delay. And that's two lasers operating independently but on the same sample, so it's a hot probe system. It's one of the most versatile ones around. Octopus is a suite of mainly biological instruments working around a central pool of lasers, so you can generate pretty much any wavelength you want for things like optical microscopy. The center one, Artemis, actually overlaps both of these, and this produces close to attosecond pulses, that's 10 to the minus 10, of light, which are then frequency doubled using high Harman generation to give very soft X-rays. So this means you can now generate using lasers very soft X-rays with attosecond pulse rates. So this is going on to the areas of electron dynamics and so on. So it's very soft pulses. The area that's probably interesting to this community here is octopus, where we tend to look at biological samples using fluorescence techniques. And here's an example. The sort of techniques that we have are super resolution microscopy, single and multi-photon, confocal, fluorescence lifetime, and so on, and sort of images that are available are demonstrated there. Onto the other facilities, the neutron facilities. These are actually quite interesting because neutrons use the same techniques as X-rays. So a lot of the time people get a little bit confused as to why would anybody ever want to use neutrons. For a number of reasons, they're highly penetrating, so they can go through fairly large sections of steel where X-rays can never do. They're non-destructive. They're atomic level interactions, so you get slightly different information than you would do with X-rays. And they're very good at looking at light elements. X-rays generally not very good at that. Neutrons actually are. And this image demonstrates that property very well. You can see it's an image of a rod inside a container. This is actually a neutron image and not an X-ray image. The difference is, if this were X-rays, you would not see anything because the container is actually made out of lead. So the neutrons will go straight through the lead, and then we stop actually by the hydrogen inside the rods. If it was X-rays, that would be a black container. So that's the difference between neutrons and X-rays. So a very useful tool. We're bringing on some new instruments onto our system. IMAT is one of them, so we hope to be able to do imaging and diffraction simultaneously. This is the sort of thing that we hope to do. So you'll be able to look at the tomography of structures, differentiate between different aspects of it. So for instance here, there's some joints, some soldering going on, and look at the different materials and so on. So that's something that we hope to be able to do. That's an image of an organic material in a rock sample. You would never be able to see this material using X-ray techniques, or in fact, have difficulty seeing that with any other technique. So that was neutrons, computational sciences. We have a high-performance computing center called Hartree over at Airtree. We do quite a fair amount of different things with the computing section. We generate an awful lot of data using from our lasers, neutrons, and so on and so forth. And over the years, that expertise has grown and grown and grown. So we do an awful lot of data handling, data storage, distribution. Big data, as everybody here knows, is playing a very large part in our activities at the moment. We have visualization suite where we can do 3D modeling and simulation, computational sciences, engineering, computational fluid dynamics and so on and so forth. So there's an awful lot of activity, particularly in the agri sector as well, going on within our high performance computing center. Another section is RAL space. I'm not going to go through the details here, but there's an awful lot of activity, often in collaboration with people like European Space Agency, Astria, Surrey Space Satellite, and so on and so forth. The result of all that activity is that we have particular expertise in sensor technology and imaging and so on. So that's something that I would just highlight here. All of our facilities are really supported by our technology department, so stuff that we need to build, develop, and so on, all of that is supported by our technology department. So the result is that we have a lot of expertise in detector systems, going from actually designing the sensors, all the way through the electronics, the acquisition systems, and so on. Advanced materials and composites, because we design high field superconducting magnets and so on, cryogenics and magnetics. This is the detector over at CERN. There's a person standing there, so it gives you an idea of the size of that detector. And that's the sort of thing that we tend to get involved in. In terms of detectors, just a couple of examples. Well, actually, this particular one here, Kirana, which is now commercialized, gave me 7 million frames per second using that sensor. That was developed in-house. To finish off with a couple of examples, this is an example of some work that was done using neutron detectors, neutron systems. Some of you may recognize this. You'll have to excuse me, I'm not a biologist by any means, by any stretch of the imagination, but one of our colleagues was looking at furandoline, so that's defense protein found in wheat. Really just looking at the properties and how it comes together and so on. And they found that actually they've used a number of techniques, neutrons, as well as dynamic light scattering and so on. And they actually found that furandoline forms micelles in the aqueous solution. It's the only protein, there's only one other protein that does this, so it's quite rare. It's an elongated structure rather than spherical. Normally these things are spherical. And it's the tryptophan-rich part that's causing this elongated shape. So that goes some way towards understanding what this protein is doing. So that's neutrons. Another example is pesticides. Because real-life systems are exceptionally complicated, what you need to do is develop a simplified model that you can compare against. And in this case, they developed a simplified model of the waxy surface on a leaf and try to understand how the water interacts with that particular model and how it penetrates into the leaves. So looking at that sort of work using neutron, they hope to find out exactly how it is that how you might make pesticides penetrate the leaf surface a little bit easier. I mentioned our space and our sensor technology. This is an AgriRover project, and actually we're doing some work with Turkey in this particular area, using a robot to remotely collect soil samples and using various techniques to try and understand what the soil is doing. It includes a camera to do some 3D mapping. And one last, I think it's the last one. I mentioned the lasers. This is looking at a tobacco plant and the structure within a tobacco plant. They were looking at how